Welcome to week 3, and this week we're going to talk about scale, technology, and energy. And the themes for today are, and I want to emphasize these points, addressing the scale of an environmental issue will help us describe the different processes over a wide range of sizes and time scales. We're going to take some examples drawn from energy use by nations, regions, and homes to compare that. One of the key points of this lecture is that net energy is the important quantity, and that's what's left over after all the losses in processing and transmission. And then we want to focus on sort of an effective scale, and that is where environmental problems that may sometimes be caused by going beyond the human scale. And so if we focus on scale, we can determine we can understand some of the causes as well. And then finally, that environmental decisions need to be made in the context of scale. In particular, are they so large and are they going to last so long that they're essentially irreversible? Then we have to have a different decision process. So today we're going to talk about scale. Let's just look at this little diagram scale. I'm going to review how it's related to systems, talk about time and space, and the Stommel diagram, which is space scale versus time scale. And then we're going to take a little detour and look at scale-effective technologies. What's that mean and why they might be important? Then we're going to focus for sort of some content on the energy and the history of how energy has helped us develop social structures, and comparison of national, regional, and home energies, and then look at net energy. And then I'm going to bring those together, looking at multiple scale perspective. And this is where looking across scales helps us make management decisions, but also helps us understand how we can build resiliency into our environment by making small-scale, reversible changes. So first, let's just compare how this scale approach is related to what we talked about last week with systems. And as we set the boundary of a system, what's the extent of what we're going to study in a system? This is essentially setting the largest scale that we're going to look at. And these two examples don't really do it justice because they're about whether it's a deer or the food in the deer and the feces, but it's the same idea that the boundary of the system is really the largest scale that we're going to look at. And to jump into some examples of what I'm talking about with scale, we're going to come back to this page later, but here's a couple images of how we could study scale in a forest ecosystem. And we have the time in years, and this is the log of the time in years. So 0 is 1 year, 2 is 10 to the 2, which is 100 years, 4 is 10 to the 4th, which is 10 to the 4th years. And you can see over here it's shown in more commonly used units. And what we have are characteristics of the tree stand, the needles, the crown, a patch of trees, a stand, the forest, the entire landscape. And these are given as little bubbles related to how long they last and how big they are. So in this case, needles are 10 to the minus 2 meters, 1 centimeter, and they last about a year. Whereas the landscape covers 10 to the 6 meters, 1,000 kilometers, and lasts up to 10,000 years. So those are the physical aspects. Then we look at some of the disturbances that happen in a fire. Budworm outbreaks last over decades and are at the space scale of hundreds of kilometers. These are huge things that happen throughout forests, whereas fires range in range over, just from small little fires that last for a couple days to large fires that burn off for a year or more. So this is the idea of representing what's the range of the fire disturbance, what's the range of budworm, and then over on the very right we have a list of similar climate and weather incidences of what might happen and what's the time scale of these, all the way from just a little breeze or a thunderstorm to El Nino, which takes place over a like 5 to 7 year cycle. So this is what we mean by putting all of these in scale. And this type of diagram is very useful, captures an incredible amount of information all the way from 10,000 years and thousands of kilometers down to just minutes and meters, and puts that all in one diagram so you can sort of see how all of these processes are related and the importance of looking across all these scales. Another diagram is just more about animal ecology. This might be here's the same set of characteristics of the trees, but then looking at different animals, the moose, the beaver, and the mouse, and here looking at their food choice. That's over very short time periods of minutes to hours, and just really right where they happen to be. What's their home range? How much do they move over days and a full season? And then what's their potential for dispersal? And as you'd expect, a small animal like a mouse has a much smaller range of dispersal than something as large as a moose that can really travel. So again, putting these sorts of characteristics of animals, and you can't say what's the characteristic time and space scale for a moose, because it's dispersal, it's up here. For the home range where they spend the season, it's here, and for food choice, it's here. So again, we have to be this tool forces us to be more specific about what we're talking about. All right, another characteristic that's very useful to look at for the scale is what's the texture and what are the size and distribution of different objects in the environment. So when we talk about texture, we're usually just talking about objects. And here's a good comparison. This stream here is a picture I took in Candelaria in Spain, and it's the outwash of a stream that just comes scooting down the mountain during the spring, and it moves some very large boulders. And that's because there's a lot of energy, and it can move those big boulders. You wouldn't want to be wading around in the stream when some of these, enormous boulders come rolling down with the spring flush. Here's another much more pastoral scene, although it's not a pasture at all. It's in Yellowstone National Park, and you can see a little sandbar and a very gentle stream. It's just not a lot of energy. It's not moving. It's not even moving sand very far. So small rocks and sand. So the texture of this stream is much finer than the texture of this one. And again, that's a characteristic of the shape scale, and it derives from the amount of energy that's being put into either one of these streams. Another way we might look at it, what's the distribution of different patches within a landscape. So here's a Google photo of part of the Zumwalt Prairie, and it shows some trees, some sort of grasses, and some other sort of scrub areas. This is a 50-meter difference. And just by using Photoshop, you can find, okay, what's the distribution of this dark green color? What's the distribution of this really light brown color? And you have put those in, add up the total area, and then what's the distribution? And you see the darker brown grass is the most common. There's lighter patches of brown, maybe even almost bare soil. There's green grass, and there's only less than 10% of the tree patches. But this histogram shows that this is a more representation of this landscape that we could work with and talk about before we're going to try to do some sort of transects or looking for particular animals or studying some aspect of the ecology. Okay, now I want to come back to Stommel diagrams, those large log scale diagrams we're talking about. And here's an example of one I made for a lake. And in this case, I put everything in minutes over here and meters over on the bottom, and it's a log scale, meaning here's 100 meters, here's 1,000 meters, here's 10,000 meters. And we're interested in different processes that take place in the algae in the lake. So at very short time scales, just like just dipping a bucket in there. We have photoadaptation of the algae. We have adaptation through growth. We have the blooms that happen over whole sections of the lake, and then we have the total lake circulation. Well, the way we use this diagram to say, well, what are the what are the scientific approaches, what are our methods to capture this range of activities. And we have point samples, again, throwing a bucket in a bottle, taking just a point sample. We have moored loggers that sit at one place and they record things over weeks to months. We have Landsat images, a high-level snapshot of what's happening. There's weekly sampling of the currents and a lot of other things, parameters that's carried on by U.S. Geologic Survey. And what we decided we needed was to put in these transects to connect the point samples to these weekly time samples. So we had a high-resolution data logger, and we drove from this, we drove from a particular place back and forth, created sort of a grid of intermediate data that gets at things that are about a kilometer long and at the time scales and resolution of less than a meter. So again, we use the Stommel diagram to see what are our information needs when we look at this. Okay, I'm going to shift gears for a second, and I'm going to talk about scale-effective technologies. Now, the technology includes the machine or the process, and I'm just going to say it right now, like often we think of technologies as being processes, or a machine, but it includes a lot of other things. For example, a goat could be the machine you're going to use, or you could use a weed whip. You could have that choice. So here we have these other things that are wrapped up in that technology. We have to remember that those are included. So we have the social context and the rules for use of that process. We have the information on how to use it. Maybe it's just the instructions. Maybe if it's other, how to know when and where to apply this particular technology. And then we have tacit knowledge, which is how do we actually do that? And sometimes the instructions aren't sufficient to actually know how to do something. So for example, how to use a weed whip, that comes with a little experience. How to train a goat to eat berries is quite a skill that requires tacit knowledge. So all of that is included in technology, and when we talk about effective technology, we have to remember that it might not be just some sort of machine sitting on the shelf. And then what we want to do with scale-effective technologies is target them at a particular scale in a particular circumstance. And so if we do this, we can reduce the types of waste that are involved, and with waste comes pollution and unintended damages. So some of the technology is too specific, and you need a different tool for each task. Now this might reduce the specific impact, but the overall impact of having all of those tools and all of those technologies sitting around, you might have to care. There'd be a lot of care and maintenance of those. An example of that is, what if I use just the exact type of vehicle for every errand? I'd need a hybrid car, a truck, a bicycle, maybe a pickup truck and a van, and all of those things. So that's not what we mean. We mean, what is the overall impact of this technology? And that's, again, where you might have a hybrid car to go to work, and then you have a truck that you don't drive very many miles to do specific tasks. And you have to weigh that off. What is really the overall impact? Okay, then some technology is just too large, that there's excess energy or the embedded costs in that, which seem necessary, but if there was a way around it, you could save a lot of energy. And an example I'm just going to give, I'm following this same sort of theme here, is we allow big trucks on almost every road and bridge in Oregon. And because of that, the bridges are taking a beating, the roads are taking a beating, and is it really necessary to have all the neighborhood roads built to standards that can handle enormous trucks? So in Italy, for example, they pick up the garbage with electric garbage trucks that scoot around in the alleys, and then those meet the big trucks out at the feeders. In Multnomah County, we run huge trucks up every driveway. So that's, again, an example where one large technology ends up being, that is in this case, large trucks and heavy-duty roads, ends up being a major cost, major impact. All right, now we're going to look at this later when we talk about accounting and the process of doing a life cycle analysis. And so, for example, here's a couple projects that would require a life cycle analysis to really tell which one is the appropriate technology. Should you use a horse for plowing or a tractor? It's a complicated question because you don't plow much and you need a horse. You have to feed it all year. A tractor, you put it in the barn. There's a lot of other issues that come into this. Drip irrigation versus big-scale water projects. You might have drip irrigation that only serves a little place, but after a certain scale, you might as well get water available to a larger community at really not much more cost. So again, the scale is an important part about considering whether you should have solar drip irrigation just on one site or ramp it up and have more available water. Now here's an example of a scale-effective technology that could be used for, in this case we were using it for drip irrigation, but it includes a solar panel, some volt amps controller, a local well, storage tank, just plastic, and some plastic PVC pipes that goes out to either homes or fields. This is very local. The power is generated locally. The water can be stored from just when it's sunny. It stores water in the tank. This is a very effective technology that is it's cost effective, has a minimum environmental impact, and it can be very useful in rural communities. So this includes some what you think of as technology machines, but it also includes a whole wrapper that it gets the community to buy into having to pay for and maintain this solar water delivery system. Okay, now I'm going to shift gears and start talking about energy. And the first thing I want to talk about with energy is the history of energy use, just sort of like we did with the demographic transition, but the history of energy use that had societies go from just humans living on their own to essentially where we are now in the United States with the post-industrial information age. And we can put that in terms of energy use and how that energy use allowed them to harvest resources and get access to different resources. So first, when you're a hunter-gatherer, I'm going to do this in a time scale, but it has sort of an evolution of major types of society. Hunter-gatherer, you don't have any animals. The amount of energy used per day is 2,500 kilocalories per day. That's your nutritional need. And everything you do is human-powered. Might be a little fire in there. Might be a little running water that you took advantage of somehow. But generally, day-to-day over the years, you're relying on your human energy to harvest and exploit the available resources. Then when you go into low-intensity agriculture, you have an animal, and a family might have a small cow or goat or something like that, and that animal allows them to harvest more energy and utilize more energy, in this case, in the form of grasses that are around their village, or use that to either make milk or make meat. And so the addition of that animal to the family or might be for draft purposes to carry stuff around. It's a small difference, maybe twice the normal energy that a family would use, but allows them to get access to these other resources that they couldn't. You can't just have your kids go out and chew on grass. They need have a cow or goat chew on the grass, then you get the milk, then you give the milk to your kids. Now, commercial agriculture was the next step when you stored food in one place and shipped it to some other place. So you had the farming areas and the villages, and this required moving things back and forth, keeping track. That amount of energy went into supporting the differentiation of farmers versus villagers. And again, it was maybe 5 to 20 times the amount of energy that was used. And often these villages had ways to grind corn or grind the grain, and that was maybe animal-powered or water-powered. So again, access to different sorts of resources so they could harvest the grain and store it over the year and have access to a longer eating season off that same grain, and moving water around for irrigation and personal use. Then we move to an industrial society, a big jump in the amount of energy that's used, and that's because the modern industrial society uses a lot of energy for all sorts of manufacturing, transportation, generation of electricity. You're going to see that a little later. And again, the energy jump is every human is in an industrial society shares in a 20 to 50 times increase in the amount of energy that's available to them beyond just what they eat as food. And then finally, where the United States is now in this post-industrial information age, it's at least 100 times. So just your normal body metabolism, you have, as a member of the society, you're responsible for burning 100 times that in downloading Facebook pages and other essential information age activities. So we're going to look at what are the sources, where does this energy go, and what are the sources. And we're going to do that by looking at some charts that are also in your reading in the Wikipedia pages. And I'm going to look at a few of these charts and then compare them. And this is something that you should be prepared to do. So first of all, just this graph on energy consumption in the United States shows these general things. 40% is used for generating electric power, 29% for transportation, 21% in the industrial sector, and only 10% in the residential and commercial. That means sort of like the buildings to maintain those. And we can explore this a little bit more and find out what is in each of these sectors, so it makes sense. And that is contained in this table in the Wikipedia. Down here it shows, here's a sector summary, and here's what's in those sectors. So you can see what they're actually talking about when they say residential, living quarters for private households, or commercial, what's in that sector. Now, I want to explore where that energy comes from, and I'm going to use two different diagrams. First, this one, which is a really nice diagram because it's a systems diagram of the energy generation in the United States, energy generation and use. Over on the left is where that energy comes from. Over on the right is what sector it goes to. Again, you have electricity generation, which then feeds some of these other sectors. And if you add this plus all of these up, you get 100%. But you see that all of these, with electricity generation being the biggest sector, that's redistributed across some of these other sectors. But those are huge, electricity generation, transportation, industrial are really the large sectors. The other thing I want you to notice about that is with each amount of energy that's generated, there is waste associated with it, and that waste shoots over here to what they call rejected energy. So of the total energy services that are available, we get 37 quads in energy services that are used, and rejected energy of 58. And so this is the efficiency of the overall process here. Okay, now let's look at another diagram that's similar to this, but a little bit more direct and easy to understand in terms of here's the supply and here's where it goes. So the supply, petroleum being, oil, being distributed between all of these sectors. And again, 72% of the petroleum goes to the transportation sector. So there's a huge transportation sector is the second largest, but it really takes a lot of petroleum. Then down here, electrical power draws fairly evenly from a lot of the different natural gas, coal, renewable energy. So you can see just at a glance how some sectors are really dependent much more on one supply of energy. And again, that's pretty obvious because transportation requires storable, mobile forms of energy, which oil and gas represent. There's really no coal generated. You can see there's no coal-fired transportation at this time, as there used to be. Okay, let's look at another couple of graphs here and do some comparison. And the one I wanted to compare was what's the energy that it takes to run an economy. And in this world energy consumption graph, we see one graph here, which is how much energy per dollar, equivalent in these countries, how much energy do they need for a dollar. And you see Norway uses the highest. Then there's a whole bunch of countries pretty much the same, including US, and then down here dropping off. And this is per dollar in the economy. I'm going to come back to that in just a second, but I'm going to compare two others first. One is in fossil fuels. I want to look at these two graphs, and then you can think about that graph I just showed you. One is fossil fuel usage per capita, and this is given in the annual tons of carbon emitted into the atmosphere per person. And you can see the United States is very high on this. But again, we're normalizing per capita. So when you look at countries that are quite a bit larger in population, such as China than the United States, it's a little difficult to interpret, but in any case, this shows huge amount of carbon output per person in the United States. Okay, now let's go down in this same article and look at economic efficiency, similar to what that other one was, which is here's the GDP dollars, essentially the size of the overall country's economy compared to the carbon emitted. And in this is sort of flipped. Which country gets the most GDP per the amount of carbon emitted? And here you get Brazil and France having really high efficiency in turning carbon emissions into dollars. And then out here on the other end you have countries that really their economy doesn't do as well compared to how much carbon they're emitting. So the point of this me going through these figures is that it's really important what you're normalizing to. This isn't just total carbon emission, it isn't total GDP, it's almost all of these graphs are represented as a ratio of one to the other. So that's something that you should pay attention to on the assignments page is when you look at those graphs, what is it you're really comparing? Try to understand what's being compared and what the point of that comparison is. Okay, another important concept in this course is this idea of net energy. And that's really the important thing is for the return on investment, what's the net energy that you get? And it depends on the efficiency of each step and the number of steps. And if you took 101, it's like the energy pyramid. And here's a little systems diagram of each case. How much energy gets passed from the energy stock to the first process, to the second process, to the third process. And you can see that if you have high efficiency in just a few steps, you pass a lot of energy across. If you have low efficiency in more steps, you pass almost hardly any energy across. You might think 30% energy transmission is really pretty valuable, but we got 3 steps of 30% put in series. You only get 2.7% of the energy stock available for the final use. And it's the net energy. It's not what's here. It's not what's in the energy stock. It's what you can use it for. So this is an important concept that relates to scale in the sense that if you have bigger scale and energy projects and you have to transport energy all around, that is going to require more transformation and more steps than if you can generate energy right at the end use point. You can have a solar panel that's only 30% efficient and generating energy right at the end point compared to having a whole process of very high efficiency, high technology ways to use oil to generate electricity, move the electricity through the transmission line, and finally use it. So this is an important thing to remember, and it relates to scale in the sense that like the number of steps relate to the overall scale. Now, sort of as another point about fossil fuels, we need to understand where they come from and what they, because we're talking about petroleum, coal, natural gas, these forms of fossil fuel. And we often hear that they're talking about reserves. And the reserve, really, there's several characteristics. I'm going to show you 2 graphs, or 2 visuals on this. One is this one that's right in the notes. And here we have how much of that energy for coal oil or natural gas, how much is undiscovered and discovered. And then what's the cost of getting at that? So if it's very low cost and it's been discovered, then we call that reserves. But we could have discovered some sources that are higher cost because they require some technology and money to be employed in order to make those feasible, and the cost of the cost of that fuel when it gets to market may be too low. So an increase in the market value of oil, coal, or natural gas would actually open up reserves. So a reserve is a very dynamic idea, and we can see that over here in the in this wiki page on oil reserves. There's a really nice diagram that represents fossil fuel reserves in terms of a probability that there is more than that. And so here's a curve that shows what's economically recoverable, here's technically recoverable, and here's that we know where it is. And so in each case, there's more of a probability distribution around it instead of just a sharp line between the, in a table like I'm showing here. It means there'd be a fuzzy line here and a fuzzy line here where the reserves are based on the economics of it and based on whether it was discovered or not and the cost of that material. Okay. So now I'm going to shift gears into going back to where we are in the overall lecture. We just talked about this, nanoenergy and this sort of stuff, before we talk scale effective technologies. Now I want to talk about what's the impact, or what can we learn by bringing those two things together. Here we have energy and scale. What happens? What can we learn by bringing those together? And the first thing is sort of a minor point, but we have the amount of energy that we use in a particular area is the energy or power density. So if you have a very high energy zone, such as like the inside of a reactor or a freeway with cars driving really quickly, that energy that's being used there has to dissipate out. And the more concentrated you make this energy zone, the higher density this is, then the more effect that energy has as it dissipates out. So if you think about a road, we have high energy cars going by, using up a lot of energy, very high energy and power density. Then there's this dissipation zone. Anything that's in that area is going to get hit by a car or the road pollution. Then you get out into a stress zone. Well, there might be a few little plants or something that lives there. And then you finally get to this natural energy level where the impact of that particular energy use has dissipated out below the natural energy level that controls the sort of fabric and texture of the environment. So this concept is important when you think about how humans tend to concentrate energy in one particular spot, and it leads to not just an impact on that one spot, but like this whole dissipation zone. You see it with hydro projects where you put up a big dam and then you get erosion and changes in the water, the river system quite a ways out. You see it with roads. You see it with a whole variety of human activities where concentration of the activity is one part of it, but then you need to consider how that affects the rest of the scale of the environment. Okay, now another real important point for us in this class is one of the things we call the precautionary principle, and that principle states that when there's uncertainty or you fear that what you're ever going to do is irreversible, you need to be very cautious, and you need to study the problem a lot more, and you need to try to understand what are all the possible impacts and avoid negative impacts. So the idea of the precautionary principle is when it's uncertain, avoid the worst possible outcomes. And that relates to scale. If we look at projects that we might propose in terms of spatial and time scales. Spatial, we could have local versus full ecosystems, and the time of reversibility. How long, if you go and do something, how long does it take for that to really go back to how it was before? So if it's local or even if it's fairly large but reversible, then you can apply this cost-benefit analysis, which just means what are the costs of it, what are the benefits. It's not just a simple ratio, but it pays attention to all of those things. So it's more a financial argument. If it's either really large or it's multi-generational in its impact, then you should apply the safe minimum standard, which is a sort of another formulation of the precautionary principle, which means avoid the really downside risk because it's irreversible. Whatever you're going to do, if you do that and it has some unintended consequences, that's going to be severe. So again, this is using essentially a Stommel diagram to relate areas where you would use precautionary principle if it's irreversible, or otherwise proceed with cost-benefit analysis and get the most benefit. And that just means, that might include reducing pollution as one of the possible technologies to use. That would be included in the costs and the benefits. All right. The other part of this is going back to that diagram of projects across scale is what we call the panarchy or cross-scale diagram. And in this case, panarchy means pan-hierarchy across the different levels of organization. And I'm going to spend just a minute explaining this, that if we want to study panarchy, we have processes that exploit resources in a natural environment. And what I'm going to use is an example of a forest. So during this exploitation phase, the forest is growing very rapidly. Then it moves into conservation phase. This is when it gets near the carrying capacity, ends up being slowing its growth, increasing the connectedness, slowing the potential for new growth because it's really reached its carrying capacity of the population. Then some disturbance comes along, like a forest fire is a good example, that releases a lot of the nutrients, and it decreases the connectedness. Instead of one big patch of trees, now you have sort of a bunch of trees that are burnt and some that may not be burnt. But it also it goes to a low potential, but it provides resources for there to be reorganization. And this reorganization phase is like the soil building after a forest fire, the initial steps of grass establishing themselves to sort of lock the ecosystem into a positive cycle, and then you get exploitation again. Now, this is across scales. The exploitation happens at very small scales and is not sort of connected. You can have a wide diversity in how this starts out. Once it gets out here into the higher connectedness, it means it has to be across a larger set of scales. So the point of this is, just like what I was talking about just before, this idea of reversibility. Once you get up into this area, the only way to reverse it is through like a large-scale release, and that meaning a large forest fire across a larger area. And then that goes into reorganization again at a smaller scale and leads to the regrowth of the forest. So just think about the forest metaphor for a bit. You can see how this all fits together. Okay, so for our decision processes, as we set something up, it's the same idea. If we make small decisions when they come into this conservation phase, if we have say we have a forest and we harvest certain portions of it, we're doing that release in a small on a smaller way and letting the system reorganize itself. That's what a mosaic would happen, or these intermediate disturbances that happen, small fires, lightning strikes, small wind events. If you wait till the whole system is locked into this conservation stage, like one big forest that's all connected and you need a massive fire, again, that's generational, large scale, it's less reversible. So this diagram is, and it's called the panarchy diagram, it's a really good way to think about that, how to avoid traps by having smaller scale disturbances and running through this exploitation conservation process and having some of that release sort of continual renewal instead of locking in one big solution. All right. Now, I have two more things I want to talk about right now. One is just some comments on what happens if we fail to account for scale, and then the third, and then that'll be the end of this lecture. So if we fail to account for scale, one of the things that can happen is, this is one of the proposed reasons why civilizations collapse, which is they don't realize what the scale of all the processes are. The processes get so big and connected and complex that they just can't pay the overall cost of having those large civilizations. Related to that is that there is pulsing in natural processes, the constant upswing and downswing, just like we saw in the panarchy diagram. There's a range of processes always going on, that sort of pulsing, and it could be that this pulsing is a natural condition that needs to be preserved. And you can see a couple examples of long-standing populations that may have maintained their longevity as civilizations because they pulsed. For example, Italy is never really locked into any particular form of government or seat of power. It shifts all around all the time. And so that country, that sort of civilization that went from Rome all the way to modern Italy, has maintained many characteristics of that civilization because it has pulsed, because it's gone through good times and bad times, maintains sort of a longevity that way. Another is the example of Easter Island. We always think about Easter Island as being this society that collapsed. But again, over the long scale, what they were able to do with that island is there was cultural elaboration. During periods of good time, they would create these statues. During periods of bad times, they would hunker down and try to grow more food to feed their families. So they had an outlet for their activity in the good economic times. That's just one theory, that cultural elaboration actually allowed them to persist over many centuries instead of some of the other small islands that just collapsed. Now, this is difficult. This challenge of looking over larger timescales is really difficult for humans. So, for example, the human brain is not necessarily designed to handle certain types of processes very quickly. And one well-documented case is acceleration, or deceleration rather, when you're going quickly. Humans evolved in times when they might be going 15 miles an hour maximum. To be going 60 miles an hour and try to understand deceleration is a real challenge for the functional part of the human brain. You can go and get your calculator and calculate how long it would take, or if you drove a lot and hit the brakes really hard. But it's often just a underestimate of how fast you can stop. And this comes because there's really no experience built into the human brain. So Reed talks about this, and he says that this underestimate of your ability to decelerate rapidly may deviate from what is optimal or efficient, meaning you crash. Another thing is that it's been shown that human brains have used different parts of the brains for different types of decisions across time. Short decisions are made with one part of the brain, and longer-term decisions are made for another part of the brain. So you can ask people to make very rational comparisons between, so for example, taking out a loan or gambling, and they will make different decisions if you give them different time horizons. So I just want to mention this because it's one of those things you need to consider. Why do we have this impact on the environment? And it's one of the reasons it's very difficult to think across these different time scales. And let me just finish up here with just some examples of that. We have, you can think about your life in terms of periods of time that you spent, and you were making different decisions over those periods of time. So for example, if you're a parent, like I am, you grew up as a kid, you made some sets of decisions. You went to college, you made another set of decisions. When you started to have children of your own, you made a whole different set of decisions. Each one of those was very in the moment over periods of time of of 5 to 10 to 15 years. None of them were life cycle decisions. Only people who are older and have been through all those can then integrate, if they feel like it, over that long period of time. And yet 5 to 10 years is nothing compared to environmental timescales. 5 to 10 years is just what it takes to start growing a wetland back or start a stream restoration. We need to be able to think on timescales of 50 to 100 years in order to do that. So this is a real challenge for humans in our society, and in some ways, to talk about the human brain. So it's something to really pay attention to as you say, well, the environment's so messed up, and why did they make these decisions? Well, a lot of you can say, well, what was the time scale that they were expecting of this decision to take place? All right. Now, the only thing I want to say to finish up this lecture is that one of the things you should check out is in D2L is the week 3 crux examples, and make sure you look at the learning objectives and those crux examples before you move on to the concept quiz and the crux. All right, thank you.